Okay, so hello everyone. I'm Georgios Hadjidemetriou. I'm a research associate in CSIC and in the asset management group. The topic of today's presentation is maintenance and planning of resilient transport infrastructure. Before starting with the main part of the presentation, let me quickly introduce myself. I'm a civil engineer. I have a master's in project and enterprise management. My PhD was a Marie Curie funded project. It was about automated monitoring of road pavements using computer vision. And it was a collaboration between 3 universities. And then after the end of my PhD, I came back to Cambridge for my postdoc. Finishing soon, and I'm starting a new position as a senior research associate for the Digital Roads of the Future project. I will be coordinating the data science team, and I will be working from the civil engineering building, so I'm coming closer. Before focusing on SafeWay, which is the subject of today's presentation, I wanted to give you a very quick overview of a project that we have been working with Jennifer the last few months, and also of the project that I will be working for the following years, just in case some of you see any potential synergies or they want to ask me something about those projects at some point. So this project is called Line of Sight, and as some of you may know, is the continuation of the PhD work of James Heddon. It's funded by CDBB and Costain. It's a 12-month project, and we are supposed to finish at the end of March. It's related to asset management organizations that they have to manage thousands of assets and also a diverse set of stakeholders, while at the same time they try to reduce financial and environmental resources while increasing their social value. So the aim of this project is to fill the gap between organizational information requirements and asset information requirements. And the novelty is the identification and understanding of functions of asset systems that impact organizational objectives, and then of functional information requirements. This is a quick overview of the Digital Roads of the Future, which, as I said, I will be working for the following years. The partners are Cambridge, Costain, and National Highways. The project will last 5 years, and more than 50 researchers will work on that project. Funding is coming from 2 different sources, from EPSRC and from EU. The project aims to increase the resilience of roads that they can measure and monitor their own performance over time. It also aims at safer and greener roads. So EPSRC funding is 8.6 million, and the EU funding is 5.9. The EU fellowships will be provided to postdocs and with duration of 36 months. All of these researchers will be divided into 5 different teams: smart materials, automation and robotics, data science, digital twins, and sustainability. And all of these teams will be working together with the same aim of improving the resilience of roads. Okay, this is the outline of today's presentation. I will start by presenting the background of SafeWay, and then 3 methodologies that we developed in CSIC for the SafeWay project. And at the end, I will present the highlights and work in progress. Only in the European Union, goods transport equal more than 3,000 billion ton-kilometers yearly and around 6,000 billion passenger kilometers. The majority of this is on roads and railways. However, European infrastructure networks are currently in insufficient condition due to low investments, and that's why they have high risk of accidents and in some cases low performance and low availability. In addition to that, climate change will increase the frequency and intensity of extreme events and thus the possibility of a disruption. And disruption on a transport network may cause loss of reachability to areas of interest, traffic rerouting, and reduced productivity. So the aim of SaveWay was to design and implement strategies and tools to increase resilience of inland transport infrastructure by reducing vulnerability to extreme events. By inland transport infrastructure, of course, we mean roads and railways. So the project was a 42 months project, started in 2018, finishing this month. The budget was 4.5 million. We were 14 partners from 8 countries around Europe. The partners included universities, technology companies, and asset owners. Extreme events can be divided into natural disasters, including heat and cold waves, floods, landslides, droughts, wildfires, and windstorms, or man-made events consisting of terrorism, vandalism, and accidents. The project used 4 criteria for evaluating resilience of infrastructure: robustness, resourcefulness, rapid recovery, and redundancy. And it also focused on 3 dimensions of the disaster management cycle, which are preparation, response and recovery, and mitigation. Preparation is all about prediction, monitoring, and developing decision tools. In CSIC, our focus was prediction and decision tools. This was our contribution to SaveWay. But SaveWay was also focused on response and recovery by real-time optimized communication with operators and users, and also mitigating the impact of failure by using resistance and absorption of the damage impact. So these are the different work packages of SaveWay. As you can see, they include risk analysis, infrastructure monitoring, crowdsourcing, predictive models, decision support systems. All of these are the input to the IT platform. And then we have an action plan for improving resilience. The applications that I will show today are related to predictive modeling and to decision support systems. First methodology that we developed was the maintenance prioritization for bridge elements, considering not only the condition of bridge elements, but also their criticality within the network. So state of practice in transport infrastructure asset management can be divided into different stages, and every transportation authority has their own guidelines and their own steps that they follow. But these are some steps that most of the transportation authorities follow for managing their assets. So they normally start from condition monitoring, which could be manual or semi-automated, in some cases fully automated. And then they use deterioration modeling, cost-benefit analysis to decide what are the optimal maintenance activities to apply. And then they may evaluate their service and resilience of their infrastructure, and based on that information to plan a new network layout. The focus of this work is bridges, because they are not only critical but also vulnerable elements, normally positioned at intersections of roadways or railways. Maintenance prioritization of bridges face some major challenges. One of them is that there is a wide diversification amongst bridges, bridge elements, and environmental conditions. Also, in most of the cases, inspection data is limited, since bridges are inspected every 1 to 7 years. Also, the criticality of bridges varies in a network, since it depends on traffic or the areas that they connect. So asset managers, they have to decide what's the optimal maintenance timing, while at the same time, they have to satisfy safety and budget constraints. Our objective was the development of a predictive maintenance prioritization method for bridge networks based not only on their condition, but also on their criticality. Our method can be divided into 6 main stages. First one is Deterioration Model. It starts with clustering of data based on most relevant features. And we do this to address the challenge of having few inspection data for individual bridges. And then we apply Gaussian process regression, which is a non-parametric technique. And it is capable of quantifying the confidence of our predictions, since it uses kernel functions to fit marginal normal distributions for the output variables. This figure is from one of our case studies. In the y-axis, we have the condition index, which ranges from 0 to 100. 100 is excellent condition. And in the x-axis, we have the age in months since the date of construction. Red color line is the predicted condition index, and the gray area is the standard deviation. The narrower this area is, the more confident we are about our predictions. And we can see that in areas that we have a lot of data points, we are more confident about our predictions. In this example, we see the condition of a bridge deck. We had 300 data points, around 300 data points divided into 4 clusters. So this is only one of the 4 clusters. The clusters were based on the deck material as proposed by bridge engineers for the classification. And then we use 80% of the data for training and 20% for testing. And then 5-fold cross-validation so that we test the entire data set. Our mean absolute error was around 8.4%. Moving on to the second stage of the methodology called optimal maintenance predictive model. Here we use life cycle cost analysis, and the output is the long-term average cost of bridge elements. In these figures, we have in the y-axis the cost, and in the x-axis the time in terms of months. We have 3 different trends. In the first one, we can see that the cost is increasing over time. So the sooner we apply maintenance, the better. In the second example, we see that the long-term average cost is decreasing over time. So we don't really have to do anything. And in the third example, we have a minimum point, which is the optimal time for applying maintenance. The third and the fourth stage of this methodology, called penalty cost function and group maintenance, aim to simultaneously maintain different elements belonging to the same bridge so that we will reduce the setup cost and the traffic interruption. In this figure here, we can see that the optimal timing for element 1 is time 1, and for element 2 is time 2. So we're trying to find a time in between those times to maintain them simultaneously. To do that, we use a penalty cost function, which is able to estimate the impact on safety if maintenance is shifted in terms of money. And then we use a genetic algorithm to compare the reduced cost due to grouping with the safety risks. So if the first one is higher than the second, then we go ahead and we conduct grouping. And the output is the optimal maintenance time for each group of elements. Next stage is the criticality-based prioritization of our bridges. So we want to have a ranking of the bridges based on their criticality. The input here is the location of bridges and municipalities, the distance between them, and the traffic that they serve. Here we use complex networks, and we have two different metrics to evaluate criticality. First one is the traffic that bridges serve, and second one is what is the extra distance cost when we remove the bridge from the network. This is again an example from a case study. This area is in Portugal. The green color nodes represent bridges and the white color nodes represent municipalities. Here is the developed complex network. Then the size of the nodes is proportional to the population. So blue color nodes are the municipalities, and then we have green, yellow, and red color nodes representing bridges. The red color shows the most critical bridges, and the green color represents the least critical bridges. Final stage is scheduling. I included this small table to explain how it's conducted. In reality, this table is way longer because it includes all the bridges of the case study and all the elements of the bridges. So first column is showing the bridge ID, second one the element ID, third one is the optimal year of maintenance for individual elements, and then fourth column is the optimal year of maintenance for groups of elements. And I selected these three groups because all of them are supposed to be maintained in year one. And this column shows the criticality-based prioritization of bridges. So bridge number 1 is ranked as 12th. The second bridge is ranked as 13th, and the other one as 21st. And in this example, we didn't have enough budget to maintain all of group elements in year one. So one of the group of elements should move to the following year. So in this case, the one which is ranked lower in the criticality ranking is going to be maintained on the second year. And in this case is the third group of elements. Moving to the second methodology that I will present today. And it's about the planning of, I cannot see the title now. Anyway, it's about the resilience evaluation of existing infrastructure and how we can plan a novel infrastructure. Resilience, there are different definitions of resilience in the literature. One of them says that resilience is the capability of a network to prepare for, absorb, recover from, and adjust to disturbances. And in literature, we can find that there is a direct connection between resilience and connectivity of a network. When we try to evaluate the connectivity of a network and plan a new network layout, we face some challenges. One of them is that we need to follow a network perspective to understand failure propagation and traffic rerouting. Second one is that there is a significant variation of nodes and links criticality based on the traffic that they serve for the impact of their failure. And last one is that there is no standardized method for assessing resilience and planning network layout. The aim of this methodology was to evaluate network connectivity and propose the development of optimal alternative routes to improve connectivity and consequently resilience. Our method can be divided into 3 stages. First one is spatial network extension. Sorry. So here we basically design all the possible new roads that can be developed in our network. we have two types of nodes, nodes A, which represent municipalities, nodes B that represent bridges. And our the solid line links are those representing the existing road network. And the dotted one represent dummy roads, which are the all the potential new roads. Second stage is about evaluating network connectivity using our own developed metric called ABA closeness. It is based on closeness centrality that approximates the distance between a node and rest of the nodes of the network, and thus the level of isolation of the examined node. So when this distance is high, we have high closeness centrality and poorly connected nodes and high levels of isolation. In our case, we use the ABA closeness, which is able to measure the distance for routes starting from a node A, so from municipality, passing by a bridge and ending to another municipality. The final stage is called optimal road section selection. Here we use a genetic algorithm, and the outcome is a set of K new roads to optimize ABA closeness and to improve resilience. The new roads are chosen among the set of all new potential roads, and the user set the number K of new roads based on budget and on physical constraints. This again from the case study in Portugal. We can see the developed complex network. Blue color nodes are the municipalities, yellow color nodes are the bridges. The black color links are the existing roads, and the gray color links are all the potential new roads that we can develop. For this example, we use Python. Processing time was 2 minutes. Data is coming from infrastructure of Portugal, which is the organization managing roadway and railway infrastructure in Portugal. In this example, we had 21 bridges and 12 municipalities. And these are the results for developing 3 new roads and 5 new roads. For 3 new roads, we can see that ABA closeness is reduced from 0.57 to 0.35. So our connectivity is improved. And in the second example, we can see that it's reduced from 0.57 to 0.31 by adding 5 new roads. In this example, we can see that we don't have to add a very high number of new links to improve connectivity of a network. With 3 new sections, we have a significant improvement of connectivity. Moving quickly to the third methodology, which is about infrastructure flexible planning. So the challenge in planning infrastructure is that there are high levels of uncertainty in technology, population, climate, and economy. Here we try to use a methodology called dynamic adaptive policy pathways and apply it to the road and the railway network. This methodology is normally used for designing policies related to flood risk management, because these policies need to be flexible and dynamic due to changing physical and social parameters. The methodology is divided into 10 stages that I will not get into detail because it will take a lot of time. So I will directly go to our case study, which was the connection between London and Manchester. We can see with red color the road network and with gray color the railway network. So in this figure, in the y-axis, we have the number of passenger journeys during morning peak time. And in the x-axis, we have the date starting from 1995, going to 2040. Blue color are the road journeys, red color are the rail journeys, and gray color are the total journeys. So here we can see the capacity, the existing capacity, and the capacity that we will have in the future if 6 potential actions are going to be applied. These actions are related to new projects that they will increase the capacity of the network. And then we can also see the demand, the existing demand, and then the projected demand for using the roads and railways connecting London to Manchester. So this figure is helpful to find points in time where capacity cannot serve the demand. Here we can see in the y-axis the 6 identified development actions. First one is the use of 11-car trains. Now, most of the trains are 9-car. Then is the development of HS2 phase 1, HS2 phase 2, operating M1 and M6 as smart motorways, having infrastructure for electric vehicles and having infrastructure for autonomous vehicles. This kind of representation and this technique help us to see when an action will start and end, what is in construction, what is in operation, when do we have demand over capacity, when are the major decision points. And for this case study, our selected and proposed path is showed in red color line. And it shows what action we propose that need to be followed. But the good thing about that is that flexibility. At any point, you can decide that you want to follow a different direction if something is going to change in the future in terms of population or climate or economy or even technology. So the highlights of today's presentation regarding the maintenance prioritization method, we noticed that we have improved the results after clustering for our deterioration model. It is applicable to any bridge element, and especially when our data set is small. Group maintenance of elements belonging to the same structure can reduce the setup cost and the traffic interruption at around 10%. Regarding our second methodology, adding a limited number of optimal new road sections can significantly improve connectivity. And as we said, connectivity is directly related with resilience of the network. And so if we have improved connectivity, we have improved resilience. And finally, dynamic adaptive policy pathways is a method that can be applied to multi-project transport planning, facilitating ongoing adaptability in response to variations in forecasted demand and capacity. At the moment, we are working on several other small projects that they are related to what I have presented. We are trying to develop deterioration models considering climate change. Our predictive, we want to add the element of vulnerability to our predictive maintenance model. Vulnerability, we are going to include what is the possibility of failure and what is going to be the impact of failure. And finally, we investigate interdependencies amongst interconnected networks to estimate asset criticality, because transport networks are connected to each other, but at the same point, they are connected with power networks or with telecommunication networks, for example. So that's the end of the presentation. Thank you very much for your attention.